Did you know Kth Smallest Element in a BST is a Pattern Mastery 100 essential and a go-to question at Google, Facebook, and Amazon to test your mastery of binary search tree properties and tree traversal? Over 30% of candidates stumble on this, either by missing the in-order pattern or handling K incorrectly. Nail this problem, and you'll be ready for everything from ranking queries to real-time analytics. Let's use the basic framework to tackle Kth Smallest Element in a BST step by step, so you'll be confident and clear in every interview. Let's break it down. Given the root of a binary search tree, BST, and an integer k, find the Kth smallest value, 1 indexed, in the tree. Input: root node of a BST, integer k. Output: integer value of the Kth smallest element. Here is a real-world example. Imagine managing a leaderboard where you need to find the Kth top performer. Or, in a scheduling app, finding the Kth earliest event among time slots stored in a BST. An interviewer might ask, how would you efficiently find the median or percentile rank in a huge, dynamically changing dataset? Let's assess. What's tricky? A BST's in-order traversal, left root right, produces sorted values. The challenge is to traverse efficiently and stop exactly at the Kth value. Think step by step. Perform an in-order traversal of the BST. Use a counter to keep track of how many nodes you've visited. Once the counter reaches k, record the node's value and stop. Be careful. Do not keep traversing after finding the Kth node. Let's clarify. You can do this recursively or iteratively, using a stack. If the tree is very large and k is small, the traversal short-circuits early. Edge cases. K is 1, smallest, k is tree size, largest. Here is the structure. Initialize a counter, starting at 0, and a variable to store the result. Traverse the tree in an order, left root right. At each node, increment the counter. If counter equals k, record the node's value and return immediately. Return the result. Now let's implement the iterative in-order traversal, leveraging the BST's natural sorted order to retrieve the Kth smallest element. We create a stack to simulate recursion. In-order traversal naturally produces values in sorted order, so the Kth value we encounter will be the Kth smallest. We enter an infinite loop, but will return once we find the Kth smallest value. This inner loop walks all the way down the left subtree. Because in-order traversal always visits the smallest nodes first, we push each node onto the stack so we can return to it later. We keep moving left until we hit a null pointer. We pop from the stack. This gives us the next smallest node in sorted order. We decrement k because we've just visited one node. If k reaches 0 exactly here, we found the Kth smallest element, so we return its value. After processing a node, in-order traversal always moves into the right subtree next. This continues the sorted sequence of values. And that's how this algorithm works. It first walks left to reach the smallest values, then processes nodes in exact sorted order until the Kth1 is found. Efficient, simple, and elegant. Let's test our function using this BST. We're looking for the first smallest element, which is the smallest value in the tree. An in-order traversal gives the values in sorted order. For this tree, the in-order sequence is 1, 2, 3, 4. The first smallest value is simply the first item in that list. 1. And that's exactly what our program outputs, 1, matching the expected result. So, our implementation is correct. It retrieves the smallest element just as intended. Now let's implement the min heap approach, inserting all node values and extracting elements until we reach the Kth smallest. We begin by creating a min heap, which always keeps the smallest value at the top. This structure allows us to extract the smallest values one by one. We fill the heap with all values in the BST using a helper function. After this, the heap contains every node's value in no particular order, but always lets us access the smallest one first. We remove the smallest element from the heap k-1 times. Each poll gives us the next smallest value. Once we've removed k-1 values, the next one we poll will be the Kth smallest. We return the next smallest value from the heap. This is exactly the Kth smallest value in the BST. If we reach a null node, we simply stop. There's nothing to add. We insert the current node's value into the heap. This ensures all values eventually end up inside the priority queue. We recursively add all values from the left subtree, and then recursively add all values from the right subtree. And that's how this algorithm works. It first gathers every value into a min heap, then repeatedly removes the smallest elements until reaching the Kth1. Efficient, simple, and elegant. Let's test our function with this BST. We want the third smallest element in the tree. Performing an in-order traversal gives the sorted order 1, 2, 3, 4, 5, 6. The third smallest value in this list is 3, and that's exactly what our program outputs, 3, matching the expected answer. So, our implementation is correct. It finds the correct Kth smallest element. Finding the Kth smallest element in a BST is one of those problems that looks simple, until you realize how much it reveals about your grasp of tree structure and traversal. This one tests whether you truly understand how BST ordering naturally connects to inorder traversal. Let's do a recap. Conceptually, the problem is about ranking within a tree. We're given a BST and a number k, and we need the Kth smallest value. Because a BST's inorder traversal visits nodes in sorted order, our goal becomes, traverse in order, and stop at the Kth step. The key insight here is that you don't need to sort anything manually. The BST structure does that for you. The challenge is controlling traversal flow and counting visits correctly. Whether you choose recursion or a stack-based approach, stopping at exactly the right moment is what keeps the solution efficient. We built the plan like this. Start an in-order traversal, move left first, visit the node, then move right. Keep a running counter of visited nodes. When the counter equals k, capture that value and stop traversing. That's the entire sorted order distilled into one clean recursive flow. We implemented that logic using either recursion or an iterative stack. Each node visit increased the count, and when the count matched k, we returned the node's value immediately. No unnecessary traversal or extra data structures were needed. Testing on LeetCode confirmed the method's precision. For k equals 3, the traversal sequence, 1, 2, 3, 4, 5, 6 correctly returned 3. Edge cases, like k equals 1 or k equals number of nodes, also worked flawlessly, proving the counter logic and traversal control were solid. The big takeaway? The inorder traversal is your built-in sorted list for BSTs. By combining it with precise counting, you can extract ranked elements directly from structure. No sorting, no arrays, just pure logic.